All right, good morning. Welcome to B-Sides Las Vegas. This track, Climbing the Production Mountain, Practical CI/CD Attacks Using CI/CD Goat, presented by Asaf Greenholts and Omer Gill. A few announcements before we begin. For sponsors, we'd like to thank sponsors, especially Inner Circle sponsors, Critical Stack and Valley Mail, and some stellar sponsors such as Amazon, Paranoids, Microsoft, etc. Even the National Security Agency. These talks are being live streamed, so as a courtesy to both the speakers and our remote audience, please silence your cell phones. If there are questions at the end of the talk, there's a microphone in the middle of the room, so please ask your question in the microphone so that our streaming folks can hear the question. And without further ado.
Okay, yeah, I think you can hear me. Hi everyone, good morning, welcome to B-Sides, welcome to Vegas, and welcome to our talk, Climbing the Production Mountain, Practical CI/CD Attacks Using CI/CD Goat. Before we deep dive into all of these attacks, let's introduce ourselves quickly. So my name is Omer Gill. I have an experience of around 14 years in hacking web applications, cloud security, enterprise security. Released some research materials in the past, like the web cache deception attack back in 2017, and a few months ago, the top 10 CI/CD security risks initiative, which we'll mention in a moment. Besides that, today I lead research at cybersecurity. We are a young startup that exists for nearly 2 years, focused on optimizing CI/CD security. Solution provides visibility and detection and prevention capabilities for possible flaws and attack vectors in your CI/CD ecosystem, similar to what we're going to showcase today.
Hi everyone, my name is Asi. I have about 7 years of experience in cybersecurity. I've been doing SOC, incident response, security architecture, and for the last 2 years I've been doing application security and CI/CD security.
Okay, so Daniel, which stands right here, by the way, he is Cider's co-founder and CDO, and myself. We have been working for several years with many organizations on improving their security posture, and something that we found was common to all of these organizations. In most of these organizations, we found many flaws and possible attack vectors in their engineering environments. And something that we found common to all of these organizations was the lack of knowledge and methodologies of how to protect their CI/CD ecosystem. This huge gap of knowledge for defenders in the areas of CI/CD led us to releasing the top 10 CI/CD security risks project. It's a big document, a 40-page document based on extensive research that we've done and discussions that we've made with some of the industry's top experts, listing and detailing the top 10 security risks in CI/CD environments. And this project, after we released it, it got some really good traction from security fellows from around the world, and it really helped organizations to start protecting their CI/CD environments. But as you all know, there's nothing like hacking on your own to actually understand how to defend against attack path. So this is why we created another project, which is the CI/CD Goat.
So as Omer said, the CI/CD Goat project was created as a learning platform. Basically, it's a CTF, it's open source, you can see the link right here, to help people learn about CI/CD attacks, try it themselves. We have 10 challenges currently in the CI/CD Goat. They cover 8 of the top 10 CI/CD security risks, and we got really good feedback from the community. A lot of people have solved it by now, and we hope you'll also try to solve it. As you can see, Rotenbar and Yarona Vital also helped us in writing the project. So let's see how it looks. So this is the environment. The whole project is based on Docker containers. We have these containers. First one is a CTFD, which is an open source used to manage CTF challenges. You'll see it shortly. We have Git, which is a source code management system, also open source. Looks similar to GitHub. It's very lightweight. The repositories on Git are connected to Jenkins pipelines. Jenkins also has a Linux agent, and the production environment is simulated by LocalStack, which is an emulator to AWS. It allows you to test stuff on AWS locally. And we have Light HTTPD, a small HTTP server. And one thing worth mentioning is that the whole project is configured as code. This also helps people to contribute to the project easily. You can easily make changes, and we have tests for everything in the project to make sure everything works as expected. And last thing, the project is inspired by Alice in Wonderland, so you'll see some familiar names.
And what we're about to do today is to present 3 attacks that attackers can execute in a CI/CD environment. All of them are based on the research that we've done in the past on a use case that we've seen in actual environments of customers that we've worked with, and on real attacks that were published to the world. And all of these challenges, we're going to present them through the CI/CD Goat project. Don't be afraid of spoilers. It's just 3 out of 10, and soon we're going to release additional challenges. And in addition, I'm pretty sure that it's going to be fun enough for you to solve it even after you'll see the solutions today. And this is our starting point. We are attackers that obtained access to a user account in the organization that granted us a user account to the SCM, to the source code management system, which is Git in this case. We have access now to some of the repositories, some with read permissions, some with write permissions, and we also have basic read permissions to Jenkins. Now, we do have some 3 challenging demos today, so I need you all sorry, it doesn't work. I need you all to hold hands and pray with us for the demo gods. We even created an illustration of 3 goats on bent knees with folded hands praying to the demo gods, facing a big bronze laptop statue in a mysterious temple, thanks to the recent Dali invitation that I just received. And let's start with our first attack for today.
Okay, guys, can you hear me? Yeah, okay. So the first attack, let's log into CTFD. As you can see, this is the platform. We have 3 categories of challenges according to difficulty, and today we'll start with Caterpillar. So as you can see, you just have read permissions. Is that enough? Use your access to the Wonderland Caterpillar repository to steal the flag2 secret, which is stored in the Jenkins credential store. Let's make it bigger a bit. Okay. So basically what we see here, that we only have read permissions to this Caterpillar repository, and we need to steal the flag2 secret that is stored on Jenkins. So let's go to the Wonderland organization. We see that we have a public Caterpillar project here. We can see that the other ones are private. This one is public. And we can see that we have some code in the project. But let's look at the Jenkins file, which is interesting for us. So we can see here, you can see from the back? So we can see here a very simple pipeline with some linting, installing requirements, and a very interesting stage, the deploy stage, which, as you can see, can only run on the main branch. So we have this stage that runs on the main branch, and it uses credentials, the flag2 credentials that we want to steal, and it uses them to authenticate to some remote server. So just to remind you, this is a public project. We don't have any write permissions on it, only read permissions, and we want to influence it somehow to execute code of our choosing. So the only possible thing for us to do is to try to fork the project and try to create a pull request, hoping that similar to other open source projects, some kind of pipeline will run on our new pull request, and maybe we'll try to execute code by doing that somehow. So we created the pull request. We can see it's on our user, and let's try to modify the Jenkins file with a malicious payload. So what I'm doing here, basically, I'll remove some unnecessary stages just to make the pipeline itself quicker. And we'll run some initial reconnaissance. Basically, we'll try to print the environment variables inside the job itself. We'll also try to access the flag2 secret and print it as base64. Maybe we'll have access to it, maybe no, maybe not. And we'll encode the flag itself. Sorry, post-COVID, everything is okay. Had it a month ago. I'll try to print it as base64. To circumvent, Jenkins has a default mechanism that masks credentials that are accidentally printed into a console output log. So we'll just print it as base64 so we can get the value itself. So I'm committing the changes, and I'm creating a new pull request to the original repository. And if we go back to Jenkins, we can see here that we have many pipelines on Jenkins. Two seem relevant to Caterpillar. We have the test and the prod pipelines. We can't see much on those pipelines because we have really basic read permissions. But we can try to scan for changes. And we see that. One second. We can see that it did detect our pull request, and it ran a pipeline. We can see that the pipeline failed, which doesn't look good. But if we look at the pipeline itself, we can see that it did print all the environment variables that we wanted. And we can see that the pipeline itself failed because it didn't have access to the flag2 secret that we tried to access. But the step before that did run. We have the environment variables. And if we look at the environment variables, we have one interesting variable. Make it bigger for you. We have the Gitty token. So we can assume this token is an access token to the Gitty server, to the source code, which Jenkins uses in order to clone the repository to the Jenkins agent and run the old pipeline using that repository. So we'll try to take this token and see what permissions, any special permissions that it has. So we'll clone the repository. Okay, so we have the repository, we cloned it, we cd'd into it, and what we'll try to do now is we'll try to commit something to the main branch. Maybe this token has permissions on the main branch. So what we'll try to do, same thing as before, we'll just delete some stages to make things run quicker. So we'll delete all the unnecessary stages. We'll leave only the deploy stage, and same as before, we'll try to run this in order to access the flag itself. And let's commit the changes. Git all is an alias that okay, git all is an alias that we made just to do a git add, git commit, and git push. And we see that we successfully pushed our new code, as you can see here, to the main branch. So that means that the token that we've used did have write permissions on the main branch on the repository, and we successfully pushed our changes. If you go back to Jenkins, I'll make it shorter for you. The Caterpillar test project won't run on it because the other one, the prod, is the one that's running on the main branch and not on pull requests. And we'll scan for changes. And we see that the main branch here triggered the pipeline. And if we look at the output, we can see here the flag that we try to print. And let's put it inside CTFD. Sorry, yeah, it's the base64. Let's decode it. Yeah, so this is the flag. And we're correct. We solved the first challenge. Woo! Yeah, let's go. First challenge. So let's talk a bit about what we've seen here. So in this challenge, we performed an attack that's called PPE, Poison Pipeline Execution. This attack has 3 variations: direct, indirect, and public. Today we performed the public one, and we'll only talk about it. So, to explain 3PE attack, we'll see an environment similar to the one that we've seen on the project itself. And we can see that we have a public repository that is connected to a Jenkins pipeline, which deploys some artifacts to AWS, which of course holds our organization's crown jewels. So because we only have read permissions, the only thing we can do to influence the project and to poison it is to fork the repository and try to modify the Jenkins file, hoping that the project is configured in a way that runs our malicious Jenkins file from the fork and not the Jenkins file on the repository itself. A good configuration would have been to run the Jenkins file from the, let's say, the main branch of the original repository and not run our Jenkins file, our malicious Jenkins file, that comes from the pull request. So what we try to do is to create a pull request. And let's see an example for a different Jenkins file. So we can see here we have 2 stages. And we can see that the build stage uses AWS credentials to run make build and make clean. And to perform an attack, we'll try to get the environment variables from the pipeline itself. And in this attack, we'll send them to a server controlled by us. Let's say if we don't have access to the Jenkins console, or this is some kind of a private project, we'll try to send it over the internet. So what we've done here, basically we poisoned the Jenkins. You can see it by the evil Jenkins that you see on the right side. And Jenkins executed a code that we gave it, and it sent us our credential that we wanted to steal. So what can we learn from this scenario? The first issue was that secrets were exposed to PRs from forks. This is generally a bad idea, and it's recommended to never do it. In most modern CI systems, it's disabled by default, but in some not. Maybe someone changed the configuration. So the solution here is to prevent access to secrets from forks. Next one is that the access token, the Git access token that we've seen in the environment variables was configured on the agent itself. I can tell you this because I know the configuration behind the scene, but this is a common misconfiguration that we've seen. People configure a secret on the agent itself as an environment variable and not for the job, for the specific job, to make life easier, but this allows any job that runs on that agent to access that secret environment variable. And the solution here is to limit access to secrets as much as possible. There are many ways to limit access for secrets. And third issue was that the access token had write permissions. The project itself didn't need write permissions on the repository, and it was unnecessary. So solution here is to limit the permissions to only the permissions that are needed. And if in any scenario you do need write permissions, maybe think it through and think if you really need those permissions. Try to avoid it. Last issue was that no reviews were required before pushing to the main branch. Basically, the main branch wasn't protected by any branch protection rules, and we can push to it directly. Maybe the maintainers of the project thought that they are the only ones that have write permissions on the project, so they don't need any protections. But as you see, we did get write access to that project, and we could push any code we wanted without any pull request reviews. So the solution for this one is configure branch protection rules on all imported branches, require at least one reviewer. 2 is the best. And that's it for the first scenario.
Okay, moving on to the second attack. Let's see what it is. It's called the mock turtle challenge. In this one, we need to objective is to push code to the main branch of the mock turtle repo, and we need to do what's needed to steal the flag 10 credentials, which is stored in the Jenkins credential store. So let's have a look at this mock turtle repository. It's right here. You can see that it's a private repository. We are as attackers that reach out to an SCM organization for the first time or to a specific repository. You'll probably want to check out what permissions we have in our hands. I can save you some time letting you know that this time we have write permission on this private repository. And our objective, again, is to push code to the main branch. I can save you some time and letting you know that there are branch protection rules in place on the main branch. Otherwise, this challenge would be too obvious and boring. So we can't directly push code to the main branch. I don't even want to try it. What we can try and do is something similar to what Asi just presented. And this is to create a pull request maybe with our own malicious Jenkins file, try to execute malicious code in the pipeline. We can see that there is a Jenkins file here indicating that it's probably linked with Jenkins. We can see that there's one stage here called PR checks, only one stage in the entire pipeline. There's lots of logic here. We can see, for example, that there's a variable called PRID being populated with the pull request that triggered the pipeline. What I can see here on Jenkins is indeed a pipeline for mock turtle. I can see that it runs on the main branch and on pull request. So it is possible, theoretically, that I can create a pull request, modify the Jenkins file, and execute malicious code in the CI. Let's check if it works or not. So we'll head back to the repository and we modify it quickly. The Jenkins file. I prepared it here. It's a simple command that loads the flag and tries to print it. Maybe this will solve the challenge. Let's have a look. Okay, so I'll quickly push this code to a new branch and create a pull request out of it. This should trigger a pipeline because we saw that the pipeline is triggered by pull requests. I'll scan it. And let's see. We can see that it was indeed triggered. Let's see what happens inside. Okay, so there it is. There's the console output of the pipeline that just finished to run. I can't find my flag here, and also I can find lots of logic here. But my Jenkins file was pretty simple, right? It just loaded the credentials and printed it to the console output. But what I see here is, if you remember, we saw that there's a variable called PRID being populated. That seems like the logic of the Jenkins file that we just modified, right? Not our own malicious Jenkins file, meaning that this pipeline, when running on pull request, it doesn't take the modified Jenkins file out of the pull request, but it always uses the Jenkins file from the main branch, which is protected, meaning I can't execute a PP attack as Asi just explained, and I need to look for another path to push my code to the main branch and to access the flag 10 secret. So let's have a look again at the Jenkins file and find this another path that we need. Okay, so this is the Jenkins file again. I'll make it a bit bigger. We can see that it loads credentials named mock turtle token. Sounds interesting, but we don't really know what this is yet. And inside, it's a bit messy. Now it's better. It's a bit small, but only this way you'll see it properly, like the flow. We can see lots of logic here. But what we mainly see is 4 if conditions. The first 3 of them check for some conditions, and then they populate variables named check1, check2, and check3 with Boolean values if these conditions are met. Then there's the last condition, checking if all these 3 first conditions are met, this command would run. Let's check it. Let's check what it does. So it's basically a curl command sending a post request to the Git API back to the source control, and it reaches the pull request merge endpoint. It sends also the pull request ID. It's the pull request that triggered this pipeline that sends this request. And this action is what sent, do merge. Now, I'm not an expert in the GD API. I'm sure that you're not as well, but I'm pretty sure that if it reaches the pull request merge API endpoint with a post request asking to merge it, it's probably an auto merge feature, right? Asking to automatically merge the pull request that trigger the pipeline. So to summarize it all, we have 3 conditions in the pipeline triggered by pull request, and if they are all met, this pull request pipeline merges this pull request automatically into the main branch. Now this sounds exactly like what we need, but we do need to find a way to meet all these 3 conditions so our pull request would be merged automatically. So let's have a look at its contents. We'll start from this third if condition because it's the easiest one to understand. It's pretty straightforward. This is it. It runs the git diff command, which checks the differences between the pull request and the target branch, in this case, the main branch. And it only presents the names of the files that were changed. And it looks for a file name version. So if I'll head back to the repository files, I will see a file named version, which is right here. It's pretty simple, pretty straightforward. A simple version. All I need to do is to modify this file in order to meet the third condition out of the 3 conditions that I need to meet. Okay, pretty straightforward. Let's head back and see the second condition. So the second condition, this is it. Sorry for zooming out. Only this way it looks properly. Okay, so this second condition, it's actually built out of 2 conditions. First one counts the number of new line characters in the version file and checks that there are 0 characters, meaning there's only 1 line in the version file, as we've just seen. It makes sure that we didn't add any new lines or remove the existing line out of the version. And the second part makes sure it verifies that the structure of the version stays the same. 3 octets with 1 or 2 numbers each. We can easily meet this condition, right? All we need to do is to modify the version file and to keep its structure. Pretty straightforward. Okay, moving on to the first condition. This one checks that these 2 variables, git_p and git_m, are equal. Let's see how they are evaluated. Make it bigger? Yeah, okay, I'll try. Even though it will look pretty crappy like that, but it's better than nothing. Okay. Okay. So what you can see here is that we have a variable called git_p, which runs git diff, again, checking the differences between the pull request and the main branch. And it takes all of the rows that were added as part of the pull request. From that, it takes only all the lines that were added, sorry. From that, it takes only the words that were added and removing redundant spaces. The next variable, git_m, which should be equal to git_p, does the same, but for removed words. So basically, what this condition does is to count all of the words that were added, the ones that were removed, and to make sure that we didn't add or removed any new words as part of our pull request. Now, as the second and third conditions are really easy to meet, this one is a bit more challenging, right? If we add our payload, it will add some new code into the pull request, and it won't automatically merge our pull request. So we need some way to bypass this condition. But if you think of it, this condition is pretty naive, right? It just checks the words that were added and the words that were removed and makes sure that they are balanced. But what we can do if we add around, 14 words in our payload, maybe we can simply remove 14 other words from another files in a pull request, right? Maybe this will work. So let's try it out. By the way, I know it sounds naive, but we didn't invent this logic. We found it on Stack Overflow, and it's a pretty popular answer. So, okay, so let's see how we can take advantage of it. So we have our mock turtle repo here. What we can do, again, we need to modify the version file and keep the structure as is. That's pretty straightforward. And we need to add our payload to the Jenkins file that will load flag 10. This is our objective, again, I remind you, and print it to the console output. So that's here right now, right? It loads flag 10, encodes it, and prints it. But now we added new words as part of our pull request, around 14 words again. So we can just head to another file, like README, which we don't care about, and just remove some words from here, like that. I can tell you a secret that I counted the number of words before I reached out to this talk today, but don't tell anyone. Okay, so I have everything saved, I believe. So let's commit it. Yeah, saved. Git all again is just a shortcut to push everything to the remote branch. Let's head to the branch that we just created called hack and create a pull request out of it. Okay, there it is. You can see pull request exists. What we can do now is to head to the mock.turtle Jenkins pipeline, scan it. The pull request should run again. There it is. We still expect it to run the protected Jenkins file from the main branch, right? Not our own malicious Jenkins file, because it's still a pull request. But what we do expect to see is that it automatically merges this pull request. Let's see if it works. So we can see that all conditions here resulted as true. And the post request using curl was sent using the mock.turtle token credential to the Git API. So we'll head back again to the mock.turtle repository, to the main branch, and we can see in the Jenkins file that we successfully bypassed the branch protection rules and pushed code through the pipeline with our own malicious payload that takes the flag 10 and prints it. Now we expect the pipeline to run again on the main branch. There it is, because we pushed new code to the main branch. And now it should run our own malicious Jenkins file with flag 10 printed. And there it is. We've got it. Let's copy it quickly, decode it. And we've got our secret, which we have to validate because we have FOMO. And that's it. Asi? Yeah, thanks. Okay, cool. So what we've done in attack number 2 is to abuse auto-merge rules. Okay, auto-merge rules, abusing auto-merge rules is where there's auto-merge rules to automatically merge our code, our pull request, our code in the pull request that we push and trigger pipeline in order to abuse the pipeline to bypass the branch protection rules on the repository side. And from there, maybe we can introduce our malicious code to these protected branches. A little bit about auto-merge rules in general, without the offensive side. Engineers use auto-merge rules sometimes in order to save some time. Sometimes they create pull requests, very simple pull requests with minor changes, and they want to skip the need of getting another engineers approving it and just to automatically merge it using the CI pipeline. Examples are simple UI changes, for example, or a version bump, as we've just seen in the example. And there are simple ways to implement auto-merge rules. One of them is to simply manually implement it in the CI and approach the SCM API like we've seen in the challenge. Another way is to use a GitHub action out of the marketplace. There are many of them to approve and merge pull requests. Some of them use the GitHub Actions bot user in order to, which is just a user in your GitHub organization, to approve and merge the pull request. Some of them request for your personal access token to approve and merge the pull request. And similar methods exist in other vendors, like CircleCI, as you can see in the screenshot, and in other vendors as well. These are examples of real open source projects that automatically merge pull requests using CI/CD pipelines. Upper one is in a Jenkins file in a real open source project, reaching out to the GitHub API pull request merge endpoint. Second one is a GitHub Actions workflow. And the problem starts when there is a logic that checks for in which conditions you should merge the pull request. In some cases, there's no logic at all that you even need to bypass. And again, this example of the naive check of words that were added and removed This is a real example from Stack Overflow. We didn't invent it, and there are many examples like that. We've seen many examples like that in organizations that we worked with. And there's a really cool use case released by in the blog post of Ryoda K, which is one of the top hackers today for CI/CD and in general. They released a blog post around how they can bypass, abuse the auto-merge rules used in the Homebrew project that you probably all know, maybe even use, to push code to the brew executable that the entire world uses, right? Pretty harmful. So our solution or recommendation is pretty straightforward, and just don't auto-merge. I mean, you can auto-merge if you can make sure that your entire logic is safe, but it's really hard to know it sometimes. Sometimes you use third-party tools that you don't know if they have any vulnerabilities inside. That's what happened in Homebrew, for example. So if you can avoid it, please do. And if not, cross your fingers that no one will abuse it. That's it for the second attack. Moving on to the third and last one.
Okay, guys, I hope you're excited. This is the last attack. So same as before. Let's go to the Dormouse challenge. Let's make it a bit bigger. Basically, in the end here, it says, hack the Dormouse pipeline, steal flag 9. Good luck. So we don't have much information about it. We can go again to the Wonderland project, and we see that we have here a Dormouse repository, which is also public. Let's see its pipeline. So we can see here very simple pipeline as before, and we can see here one interesting stage called unit tests. Basically, it runs some tests and then uses the flag 9 credential that we want to steal inside this code block somewhere. I guess it's somewhere here inside the shell script. And before that, we can see that it fetches this specific shell script from a remote location somewhere, and it executes it. So we want to somehow influence this pipeline. We want to steal this secret. Let me tell you a secret. We don't have any write permissions on it. We can't influence the repository itself in any way. So what we'll try to do is we'll try to maybe see if we can influence its supply chain, the report cove shell. Maybe we can somehow attack it. So let's go to let's go look for the project. And we can see here, we do have a project in a different organization, also a public open source called Report Cove. And it has many files here. We can also see that it has the report cove.sh file. So let's look at its Jenkins file. We can see here two stages, pull request and release. Let's start from explaining the release stage. So we can see here that it runs only on pushes to the repository itself, and it runs some, installation stages, and then it uses this environment variables, which we don't see it's declared anywhere in the Jenkins file, so we can assume this environment variable is accessible from anywhere inside the job itself. It's not the same as the first challenge. It's not of the agent itself. It's accessible by the job, that specific job. So what the pipeline here does, it writes this environment variable to a file and uses this key to authenticate to the HTTP server we've seen earlier in order to upload a new version of the report cove.sh file. So it's really interesting Jenkins file for us. If we want to attack it, maybe we can influence it somehow. And if we go back to the pull request stage, we can see that this runs on opened pull requests, on events that the Git sends to Jenkins on any open pull request. And it has two stages. It runs echo, which prints the title of the pull request, and it sends a mail to the maintainers about the new pull request. So we can see here something very interesting. We see here that it uses the title from a pull request. The title in the pull request can be controlled by us. It's a user input, and it uses it inside the bash command. So maybe we can try to do a command injection and run our code inside the pipeline. So what we'll do is, same as the first one, we'll fork the repository. We'll make some change anywhere, doesn't really matter where. And we'll create a pull request to the original repository, but it will contain an interesting title. So we're using this title. Let's see, so you can see it clear. What we're doing here, you can see the tick that starts the line. It's a command substitution syntax in Bash. Basically, it allows you to evaluate a command inside the Bash command. And we can see here that we're trying to write the same key into a file and to send it to a server in our control. So let's run the server quickly. We have a simple HTTP server that can receive uploads. So we ran the server. Let's create a pull request. And now we're doing the most important thing in hacking, is waiting. 3, 2, 1. 1. And 1. Okay, yeah, I got it right in time. We can see here that the upload was successful. And we have a new file that's called key. It wasn't here before, I promise you. We can see it's an OpenSSH private key. So what we can try to do is take that key, chmod it, because SSH likes chmod, and we can try to use that key to upload our malicious report code file, which I prepared here earlier, to the HTTP server that we've seen before. So this is a very simple line, as we've seen before. We're trying to echo the flag. That's what we're putting inside the report code.sh, and to encode it as base64. So we can see the upload was successful. And the next thing we have to do is let's go to the Dormouse pipeline. So now we're looking at the pipeline of the original repository, the open source that uses report code. We'll see the main branch here. Let's run the main branch again. So I'm just running the same thing again. It's like a rerun. I don't have any read permissions. I didn't change anything on the project itself. And while it runs, it will take some time. Oh, no, never mind. Didn't take time. So we have the challenge here, the base64 here. And we have the key. I hope everyone's ends are ready. And we've got it. Thank you. Last challenge. Okay, so let's talk about what we've seen here. So what we've seen here is we compromise a third party. Basically, we compromise part of the supply chain of the Dormouse repository in order to influence that repository and steal its secrets by attacking a different target. So what we've seen in this scenario is similar to what happened not too long ago to a company called Kotkov. Kotkov is a company that allows you to manage code coverage reports and do analysis on them. And attackers attacked it not too long ago using the similar scenario. So let's imagine you're a company that uses Kotkov. So you run their shell script inside your pipeline. What you do is you fetch the shell script that they give you from their Google bucket, and you run it to upload your report coverage, your testing reports to Kotkov. So what happened in the attack? An attacker got access specifically to the Google bucket and added a malicious line. I can tell you what this line does. Basically, it takes the environment variables and sends them to a server that's controlled by the attacker. So what happened, customers that ran those pipelines, that always, in each rerun of the pipeline, it fetches the same version of the report call file, the same file, not the same version. So what happened, they fetched the malicious new file that was uploaded by the attacker that got access to the bucket, and it sent those customers' credentials to the attacker. So what we can learn from this scenario? First issue was that the pipeline was vulnerable to command injection. The suggestion is to abstain from using any user control input in your pipelines, in shell commands, in generally in any other thing, because it can be really vulnerable and can allow people to influence your pipelines. Second issue was that the pipeline could initiate outbound connection to any address. Basically, when we sent the key from the Jenkins itself to our server, it did an outbound connection. So if it's possible, block outbound connections using an allow list, if it's possible. Last issue was no integrity check or validity was performed on the executable that was fetched during the pipeline. So the recommendation is to check the integrity and validity using a digital signature and a hash every time you fetch remote resources and run them inside your pipelines. There were also some other issues in the scenario, but those are the main ones.
Okay, there are a few messages that we can pick out from for our summary, but we picked a pretty similar one, which is that it only takes one flaw in your CI/CD ecosystem to compromise your production. Now, the CI/CD ecosystem and environments are a great attack surface and a great attack and a great opportunity for attackers, and we already see them using it and taking advantage of it in the recent years. So if you are defenders, CI/CD needs your attention. And please don't lie. I know that this is what you think right now. Thank you for attending. We do have some stickers here if you want, as you can reach out later, and we are here for questions that you can ask now or later on. Thank you, and enjoy the conference.